Hello students, today we are going to discuss about that surface tension by capillary rise method. So first, capillary tube. What is capillary tube means? Now you can take one jar, okay? So you can fill up with water, with some water. You can take the three tubes. So these three tubes are different diameter, okay? So this is one D1 diameter, one tube, and another one tube. So both are in same height only, but the diameter only different. Okay, so this is the D2, and the next one tube, this is the D3. Here D1 is greater than D2, D2 is greater than D3. So least diameter of the tube is D3. Okay. So when you immerse the tube, what happened means that water level will be rise. Okay. So this is the water level. That water level should be raised. Okay. So both these three tubes different diameter. So when the larger diameter tube having a small height alone, that water level raised. Okay. So then D2 diameter of tube water level is raised H2 and D3 H3. So here H1 is less than H2 is less than H3. So the diameter of the tube is very less means that water level should be raised. Okay. So this tube is called as a capillary tube. Okay. So it is a very small tube. For example, needle. Okay. So needle is a capillary tube. And also another one, optic fiber communication lab, we are using that YFC cable. So that YFC cable also a one type of capillary tube. Okay, so capillary tube it is very much negligible diameter. Okay, so 0.1 millimeter or 0.01 millimeter. So like that range, that tube is called as a capillary tube. Okay, do you understand? Then why that water level should be raised? Okay, certain height means by using that surface tension. Okay, so already we discussed the surface tension. So it will be called that water level. Okay, so water level is here only. The surface tension cools that water should be raised a certain height. Okay, so this is called as a surface tension. Now we are going to discuss about that surface tension by capillary rise method. Then capillary tube, how much surface tension will be acting? Okay, so in capillary tube, how much surface tension will be acting? We are going to find out that surface tension of capillary tube. Okay, do you understand? Now, consider one tube. So consider one beaker. Okay, so in one beaker, you can place one capillary tube. For explanation purpose only, I can draw the diagram very broad. Okay, so this diameter is very less than 0.1 millimeter. Okay, the diameter is equal to 0.1 millimeter. So in millimeter range only the diameter of tube is there. Okay, then that water level is here only. Okay, so after immersed in that water in that tube, what happened? That water level should be raised like this. Okay, so this surface is called as a convex surface. Okay, so when the water level is raised like this, this is called a convex surface because the angle is less than 90 degree. The angle of contact is less than 90 degree. That meniscus point is less than 90 degree mean that is called as a convex surface. Okay. Now, so this is the this area fully, that water level is increased. Okay, then now find out that surface tension, that water level rising that capillary tube by using that surface tension only. Okay, now find out that surface tension direction. So this is, you can draw a one tangent line about that point. This is the point A, and okay, now draw a one tangent line. This is the tangent line. The tangent line represents tension T. So this force always acting downwards. The surface tension force is always acting downwards because it will be impinging that water level. Okay, so that force is always like acting in downward direction, and this normal force, when the surface tension force and the normal force both are when will be equal, so that time the water level will be stable. Okay, so here that normal force is equal to surface tension force. Okay, N equal to T. So this is the angle of contact theta. This is the angle of contact, this is theta. Okay, so now like this at the point B also. Now you can draw that one tangent line. So this tangent line represents that direction of surface tension. So this will be angle theta. Okay, so here also N equal to T. N is the normal force. That normal force will be equal to the surface tension force. Then only the water level will be stable. Okay. In second lesson, we already discussed it. Okay, so two vectors in inclined position. What is the resultant vector? The resultant vector is the one common tail. You can draw the in between the two vectors. This is the A vector and this is the B vector, and this is the R vector. So R vector is equal to A vector plus B vector. Okay, so this will be split into two components. One is the horizontal component and another one is the vertical component. So this R vector split into two vectors. One is the horizontal component R cos theta, and another one is the vertical component R sin theta. So here also this is the resultant surface tension. So this resultant surface tension dissolving into two components. One is the vertical components. This is the vertical to that surface tension. So T sin theta. And another one is the horizontal component. Surface tension acting upward direction. So this is the down upward direction. So this parallel is called as an horizontal component. So this is T cos theta. Okay. So like this, here also it will be resolving into two components. One is the vertical T sin theta and another one is the horizontal T cos theta. So this will be like this. Okay. So this is the radius R, center point. Okay. Do you understand the diagram, ma? Okay. Then next we are going to calculate the surface tension. Here the surface tension acting 2 points. Two point. It will be resolved into two components, T cos theta and T sin theta. Here T sin theta both are equal magnitude but in opposite direction. So T sin theta plus of minus T sin theta. So both are having same magnitude and same opposite direction. So both are cancel each other. So only we can take that cos theta component. So T cos theta. Okay, the surface tension about that point A and B is T cos theta. Okay, so not only acting T cos theta, so it having that circumference of the this circle. Okay, circumference of this circle, what is that formula? 2 pi r. R is the radius. Okay, so that circumference of that circle 2 pi r. So the total surface tension acting that point is, so this point. Okay, so this full point. So only I can take the T cos theta of 2 pi r. Okay, then so this is the total upward force. is called as the total upward force. Then next we are going to calculate that volume, how much amount of water containing in the tube. Okay, so we are going to find out that volume of the amount of water containing in the tube. Okay, so the volume of the liquid column in the tube is, the volume of the liquid column in the tube is, so this is the total upward force is equal to like this. Okay, T cos of 2 pi r total. Now we are going to find out that total volume of the liquid, total volume of the liquid column in the tube V is equal to, so this is the how much height that water level will be raised. Okay, and the radius of the tube, because it the rising the rising water is depends upon that radius of or diameter of the tube. Okay, so that total the volume of the liquid column height, how much height, this is the height h, and radius r. Okay, plus, so this, okay, so this is the height h and radius r, plus next, so up to this one height h, you can take this. Okay, so up to you can take that height this one, and next, so not this height alone, this radius on the r, and next this area. So this volume we have to calculate. So that volume of the liquid plus this will be a one circle only. So that radius is r. So that volume of liquid column height, what is that height? This is the one circle, you know. So circle, what is the height means? There is a radius only is the height. So height r and radius r minus, so this is the total. Okay, so this will be this fully it containing some liquid. Okay, so this you have to minus it. Then the volume of liquid column height r and radius r. Okay, and minus volume of the hemisphere of the radius. So it having that water. So this will be alone. We are going to subtract that. Then only you can get that this area fully. So how much volume, how much water containing that tube. Okay. So height of the r and radius r minus volume of the hemisphere of that liquid column. Okay. Volume of the hemisphere. Then, so volume V is equal to, total volume V is equal to volume of the liquid column height h and radius r. So what is the formula for volume of the tube? So volume of the tube, what is the formula? Pi r squared h. Okay, pi r squared h plus volume of the liquid column height r and radius r. So this area, so this column, this is the radius r and this height r and radius is also r. So this pi r square into r. So height is r only. So pi r square into r minus volume of the hemisphere. Volume of the hemisphere is 2 by 3 pi r cube. So 2 by 3 pi r cube. So from this equation, pi r squared height plus pi r cube minus 2 by 3 pi r cube. So you can pi r squared height plus, you can take them away out from the bracket of pi r cube. So we can get 1 minus 2 by 3. Then pi r squared height plus pi r cube, 3 minus 2 by 3, that's equal to 1 by 3. Okay. So from this equation, you can take them out of by r square. So by r square of height plus, here r only is there, so r by 3. So the total volume of that liquid column in that tube is V is equal to pi r square h plus r by 3. Okay. So that total upward forces is equal to total downward force. Here downward force is the gravitational force. The total upward force is equal to total downward force. So T cos theta is equal to T cos theta of 2 pi r is equal to mg. G is the acceleration due to gravity, you know that. But mass, how to find out that mass of that liquid column? Okay. So how to find out means you can using the density. Density rho is the density of water liquid. So density rho is equal to mass per volume. Then mass equal to density into volume. Okay. So m is equal to, what is that density? Rho and V. What is the volume of the liquid column? Pi r squared h plus r by 3. So pi r squared h plus r by 3. Okay. So you can substitute in this equation. You can substitute this equation. So T cos theta of 2 pi r is equal to m value rho pi r square h plus r by 3 into g. Okay. So here pi cancel and r square cancel. So remaining T cos theta into 2 is equal to, here rho r h plus r by 3 g. Now we want only the surface tension. So T alone you can take that. T is equal to rho r h plus r by 3 into g divided by 2 cos theta. Here rho is the density of the liquid, r is the radius of the tube and h is the height of the tube. R by 3. Already I told that r radius of the tube is very less. Okay. So it is a range is 0.1 millimeter range. So that millimeter range divided by 3 means you can get that very least value. Okay. When compared with that height. Okay. So for example, this is the 1 centimeter. This is the 0.0001 millimeter means. So this will be a very least value. So you can just neglect them. So we can get that T is equal to rho r h g by 2 cos theta, or T is equal to h r g rho by 2 cos theta. Here h is the height and r is the radius, g is the acceleration acceleration due to gravity. So from this equation, you can calculate that height is equal to 2t cos theta divided by 2t cos theta divided by r rho g r. Here this 2t cos theta and rho g, this is a constant. 2t cos theta rho g. 2 is the constant, t is the surface tension. Surface tension of that capillary tube is also constant, and theta, angle of contact, is a constant. Then rho, density of that water liquid, is constant. Acceleration due to gravity is also constant. So you can get that height is inversely proportional to r. When you decrease the radius of the capillary tube, the height of the liquid column is high. When you increase the radius of the tube, the height of the liquid column is low. Okay, so this is the capillary surface tension by capillary rise method. Okay, do you understand, ma? It is a very important 5-mark question. Okay, thank you.